Let us now talk about the orbital momentum in atoms. So they give rise to familiar shapes of wave functions of atoms, which we all use in our discussions of chemical bonding. So for example, we have so familiar pi functions, say in this case pi x, which form molecular orbitals of this shape, which we'll call pi orbitals, or we'll have say anti-bonding states of this type also from pi states. And so this is a familiar discussion, especially for chemists who have been looking at character of chemical bonding in materials and say, for example, if you have a molecule like this, which has sigma and pi bonds, so usually you would try to discuss it in terms of, say, pi orbitals of carbon forming some bonds with s orbitals of hydrogen and then forming some sigma and pi states, say, which may be bonding and anti-bonding and occupied by two electrons shown here. And so the discussion about the nature of chemical bonds in these systems will be usually done on this language, as well as discussion of character of chemical bonding in materials. So therefore, it is important to understand the origin of that and also apply the postulates which we use so far or introduced so far of quantum mechanics in order to see how do they act actually in real life or in real simulation or calculations like that. So in order to do that, we are going to go quickly through classical definition of angular momentum. And then, according to postulates, so we need to introduce Hermitian operators for angular momentum, consider commutation relations, so to find out which of the components of angular momentum could be measured simultaneously, look at physical consequences of that, and then solve equations for eigenvalues and eigenvectors of angular momentum and see some kind of semi-classical vector model, which is, say, used for interpretation of that. And then we arrive to spherical harmonics, which are ubiquitous functions, which we all use all the time in all the calculations to describe the angular behavior of atomic orbitals. And so according to our postulates, we also need to check their orthonormality and completeness, and then use them for representation of other functions. So let's go quickly through what is important in these derivations. Obviously, first of all, we are dealing with spherical, say in this case, Coulomb potential, but it's not necessarily always Coulomb potential because we have absolutely the same mathematics for rotation of, say, diatomic or other molecules with respect to the center of mass. So all rotational spectra are also described in terms of spherical harmonics. So mathematics here is absolutely the same, and it is done in terms of spherical harmonics. So for classical particles, we have this definition of angular momentum when we have a cross product of distance and momentum. But now what we need to do is to introduce operators, which will be Hermitian operators, because we are now moving into quantum mechanical description of angular momentum. And so for doing that, we need to move for quantum mechanical representation of momentum. So quantum mechanical representation of momentum looks like this. And as a result, we arrive to this type of description of Lx, Ly, and Lz representations of angular momentum in quantum mechanics. So it's very different. So we moved from classical description to quantum mechanical description, which includes these derivatives. Okay, so the first thing which we need to do, so we have moved through, say, the first and second postulates, and so now we need to understand what are the commutation relations. So this is part of our second postulate of quantum mechanics. So we always need to check which of these, say, components of orbital momentum will actually commute with each other. So therefore, we write this commutator and calculate this commutator. And what we find out is that they never commute with one another. So that means that actually you can never measure LZ, LX, and LY simultaneously. But an important thing about them is that they do commute with a squared magnitude of an angular momentum vector. And so this commutator is equal to 0. And so the consequence of that is that different components of angular momentum do not commute. And so Lx, Ly, and Lz are not compatible observables. They do not have simultaneous eigenfunctions. We cannot have perfect knowledge of any pair at the same time. So this is basically a consequence of Heisenberg uncertainty principle, or another way of representing it mathematically. But the different components all commute with L squared. So that means that L squared and each component are compatible observables. So we can find simultaneous eigenfunctions of L squared and one component. And so this is what we need to do. We need to choose a component. Conventionally, we choose a Z component. And now we try to find simultaneous eigenfunctions of the component of angular momentum and L squared. And this is going to be LZ component. So using our postulates, now this postulate number 3, we need to solve an equation by which we take an operator, Lz, and acting on some wave function, which we don't know, which gives us an eigenvalue and an eigenfunction. The same applies here. L squared acts on the wave function, which should be a simultaneous wave function of both components, I mean Lz and L squared, and we will find another eigenvalue. So these are basically differential equations. And now we need to try to solve these differential equations. So how to do that? We need to pay attention that, say, in spherical polar coordinates, this can be done more easily than in Cartesian coordinates. So therefore, we move into spherical polar coordinates, which make some quite frightening on the first glance, say, formulae for this transformation of x, y, and z into spherical polar coordinates in terms of theta and phi. And so we arrive to these representations, which are going to be with us for a long time, for L squared, which is this formula here, and for Lz, which is a very simple formula, which is a derivative over phi. Okay, so now as far as Lz is concerned, so solving this differential equation and finding its eigenfunctions is quite easy, because now we have this type of operator. So we act with this operator on a wave function, which is a function of phi. And so we write it down here. And so what we find is that the only function which satisfies that is an exponent. And we need to normalize this exponent as usual. This is another requirement of our postulates. And so we arrive to this type of the wave function for our Lz component. So now we need to find a eigenvalue. So this is a very interesting thing, because so far we didn't introduce any quantization, although we know that it is quantum mechanics, but where quantization comes from. So it comes from boundary conditions. So boundary conditions are that the wave function must be single valued. So therefore, by imposing these conditions that the wave function should be single valued, we find, and so we need to go through derivation of that, that actually alpha, which is an eigenvalue here, should be an integer, which can take values like 0, plus minus 1, plus minus 2, plus minus 3. And in that case, our wave function is single valued. So that is an important condition. And so quantization itself doesn't come from any postulates, but it just comes from solving differential equation, which comes from postulates, and basically insisting that the wave function should be realistic. In this case, they should be single valued. You could have applied a different condition. For example, you could have said that the wave function should not be single valued. Then you would arrive to different solution. But in real life, it turns out that the solution which we have here is explaining the experiments better. So that means that, say, we are in a better shape with this type of wave functions. And so now, instead of alpha, we have m, and m is this type of integer. Okay, so now we need to look at the eigenfunctions of L squared, which simultaneously should be eigenfunctions of Lz. So now we have a much more frightening operator here, which is acting on the wave function, which is now a function of theta and phi, and it has this eigenvalue of beta. So again, we need to go through this derivation, and an important part again is that, so this is so-called Legendre equation, and so it is solved by a so-called Frobenius method. So you can go through this solution in a book, which I will recommend you later. But the important thing to notice that again, we need solutions that are finite. So again, this comes from common sense. We could introduce different conditions, but what in real life, we would like to have a finite solution. And so here we have this denominator, which will diverge if mu squared is equal to 1. But what we want is to have a final solution for mu equal plus minus 1. And so this is only possible if beta satisfies these conditions, that beta is equal L product L plus 1, where L is equal 0, 1, 2. So it's again integer. Again, this condition introduces quantization into the system. So again, it comes from the fact that we request that how our solution should look like. So the rest is simply mathematical description of Legendre polynomials. So these polynomials for different m values have, say, different shapes. So they have, say, they may be constant, or they may be much more complex. So they are so-called Legendre polynomials for m equals 0, and for non-zero m, they are called associated Legendre polynomials, which are usually described or written in the form of P with two indices, L and M. So they are quite complex functions, which depend on L and M. So you need to, again, look into that because, and get yourself familiar with these functions. I will show you some examples later. But so we see that the eigenvalues of L square for physically allowed solutions, which we requested, are having this familiar shape, L plus 1 h bar squared. And say L should be taking its, so M should be taking its values between minus L and L. So these are now two quantum numbers, which we found from solution of differential equations. For each L, there are 2L plus 1 possible integer values of M, which gives rise to familiar Px, Py, and Pz functions, or d x squared, z squared, etc. functions, which we'll see later. So in summary of this part, which I advise you to go through very carefully and through solutions, what we find is that eigenvalues of L square are equal to LL plus 1 h squared, and that M takes these values. And so these are principal angular momentum quantum number and magnetic quantum momentum quantum numbers. So we have introduced these quantum numbers, saying that we can look at the vector model, which is a kind of semi-classical representation of angular momentum on a sphere. So you can have a look into that. And then we arrive to spherical harmonics. So spherical harmonics are normalized functions, which include, say, which are eigenfunctions of L squared and Lz. which are now normalized. And so they include Legendre polynomials multiplied by the exponent, which come from solution of L squared and LZ. So they have, some of them have quite complex mathematical form. But say if we try to summarize, say how many functions do we have? So we see that, say, for each L, we have 12 plus 1 values. And so we have for L equal 1, we have minus 1, 0, 1 values of M. For L equal 2, we have minus 2, minus 1, 0, 1, and 2, etc. So these are representation of spherical harmonics in this case. And they have some specific shape. So this is a very important part. So these are imaginary functions, but you have, because they have this imaginary I here, but they have, in real space, they have these shapes which are becoming, starting to look familiar. For, say, y00, we have this spherical shape, and say for y11, we may have this donut shape or this kind of 8 or dumbbell type of shapes, which are starting to remind us so-called px and say d and f type of functions. So at the end, we need always to check orthonormality of spherical harmonics and so on, their completeness, what again can be done using say these mathematical equations, which again I encourage you to go through. And say we can see examples of these functions, which will come back later. So this is summary of what we have achieved so far in this part. And so I'm going to start from this summary in my next section, where I'm going to look at hydrogen atom, and we'll summarize it again. But this was an essential prerequisite for us to start talking about hydrogen atom, because hydrogen atom is an electron moving in the spherical potential of a proton.